Hi and welcome back. It's been a long time since I made a video, but I'm here again and let's talk a bit about thread synchronization primitives. C++11 introduced threading as an integral part of the language itself. With the new memory model, we also gained large standard library support for managing threads with proper synchronization. Let's see what synchronization primitives we have at our disposal. First, let's begin with the most basic type, a mutex. A mutex is our most basic synchronization primitive. In the standard library, it's implemented by a std mutex class, which is available in the standard mutex header. It offers exclusive access to a critical section of code and it's not recursive. Locking and unlocking is done by the lock, try-lock and unlock methods. Let's see in practice. Let's start with a bit of code. Let's have our variable which we locked as a shared memory. Let's create a mutex which will guard this variable. And let's create a thread. A thread which will essentially modify this variable. Here, let's, for example, multiply this variable by 2, and in the main thread also let's multiply by 2, and in the end let's join the running thread. Here, as you can see, we have a data race. Two threads access the same memory at the same time. This is bad. But fortunately we have our basic mutex. So first let's lock before we try to modify our shared memory and unlock afterwards. The same here. Lock and unlock. In this example, our variable is perfectly protected by the mutex and no race condition happens. Let's print it out. And let's run it. 0, because I made a stupid mistake of initializing with 0. Okay, let's turn it to 1, and let's see if we get 4. We do, without any race condition. Perfect. But you might have noticed one thing. This code is fine until you realize the code inside the critical section might throw an exception. Well, not in this case, but in general it might. And in such cases, the mutex would be locked forever. Fortunately, there is a solution for that. We have standard classes which help to lock and unlock mutex on creation and destruction. The most basic of those is a simple lock guard. Std lock guard, which is a template that takes the type of the mutex, lock, and the mutex itself. And this lock guard protects this whole scope. Okay, now we have a lock guard here, so we should make one here. Note that I'm making a new scope simply because I want my lock guard to guard this piece of code and nothing more. Okay, then let's run it. 4 again. Beautiful. So now we have a lock guard, and if you want we can substitute this lock guard for something more advanced called unique lock. It's similar to a lock guard but offers additional functionality. For now, let's just stick with lock guards. The next type of mutex we have at our disposal is a timed mutex. It's very similar to our basic mutex, but provides two additional methods, try-lock until and try-lock for. They try to acquire the lock for the mutex until a specified time point, or, like the name suggests, for some specified duration. If they succeed, they return true on success. Let's see that in practice. First, let's include our chrono header. Let's use a chronoliterals namespace. And let's use our timed mutex instead of our basic mutex. But let's change further code a bit. First, let's get rid of this lock guard. Let's change this mutex to timed mutex. But let's also move this thread in here. And inside this thread, let's try to lock the mutex for some specified time. And try lock for example, 1 second. It will return true on success. So if the lock was successful, we can perform our memory operation and then unlock the mutex. Key join needs to be here now. So why did I make this code like that? Well, if we had a lock guard in a thread here and we also had join here, you would have a deadlock. This join would wait for the thread to complete, but the thread would never complete because the mutex would be locked by this lock guard. Fortunately, in case of a timed mutex, it will only try to lock the mutex for 1 second and proceed if it fails. Let's see. As you saw, there was a delay because the mutex was trying to lock itself. It failed, so our answer is 2 instead of 4. And no deadlock. Now let's get rid of this whole code and go to a more advanced type of mutex called a shared mutex. It lives in its own header, shared mutex, and it's pretty much similar to the basic mutex but has some cool features. The main difference is that it has 2 lock modes, exclusive and shared. Only one exclusive lock can be acquired, but many shared. Also, a shared lock may be acquired only if there are no other locks. So, why the split between the 2 modes? Well, the answer lies in performance. There's a small note to that, but I'll get to that later. If you have some data shared between threads, well, which is safe to be read in parallel, you don't really need to force those reading threads to wait for each other. They can all perform the read with no data race. Remember, reads are generally safe, or at least should be safe. On the other hand, reading such data while it's being written results in a data race. In such case, all reading threads must wait for the writing thread to complete, and then release the lock. These 2 situations imply that reading can be protected by a mutex locked in shared mode, but writing must be locked in exclusive mode. Let's see this in practice. Let's create a class, let's call it widget, and private. Now let's assume this has some data. In data equals 0 and some access methods. Data constant data and the classic many typos today, set data value data equals value. Great. Now let's create an object of our class, and now let's observe what happens when 2 threads try to read the data and 1 thread tries to write it. So we have 1 thread which will write the data, which essentially means it will simply read that memory. Let's create another thread, T2, which will also read this memory. Let's join them both here. Like that. And let's introduce a data race. Let's set data here. So this is a classic example of a data race. We have two threads reading a location in memory and one thread at the same time potentially writing to that location. So let's assume widget should be internally synchronized, so let's synchronize it. Let's create a mutable because this is const, and you'll see why. It's the shared mutex and mutex. So what can we do with it? In set data, we need to acquire our classical exclusive lock. Let's use unique lock for that. Shared mutex lock mutex. Unique lock, as the name suggests, locks the mutex in a unique ownership lock, in exclusive lock mode. But with get data, we can use something else called a shared lock, which locks the mutex in a shared lock mode. So what does it mean in practice? This means two threads calling get data, these two, will both lock the mutex in a shared lock mode, which means they will not wait for each other. And that is because this data is only being read, there's nothing written, there is no data race, reads are safe. Const implies that calling this from multiple threads should be safe, and this mutex ensures that. So these two threads can pretty much read this value from memory in parallel and nothing bad will happen. But when this thread tries to write the new value, the mutex will be locked in a exclusive or unique lock mode. So any other lock will simply wait until that lock is lifted. Let's see. And you have two threads printing 0, 0, and that's it, because they managed to run before set data managed to set this data to 1. The main point here is that there are no data races anywhere, both during reading and writing. As for the performance aspect, well, shared mutex can be faster than a typical mutex when you are read heavy. When multiple threads are reading the same memory location, it might be faster to use a shared mutex because the threads then will not wait for each other. But a shared mutex could be, and generally is, a bit slower than a standard mutex. So if you have mixed reads and writes, well, you might consider using the most basic mutex there is. We also have another type of mutex called a recursive mutex. A recursive mutex and recursive time mutex is a variation of the basic mutex. The difference is that one thread can acquire the lock multiple times without deadlocking. Other threads will block in a normal way. To be fully released, a recursive mutex needs to be unlocked the same number of times it has been locked. Use this only when you know a given mutex could be recursively locked by one thread and there is no other way around it. You may need to design your synchronization some other way to avoid recursive mutexes, because in general they might imply that something is bad with your design. But nevertheless, recursive mutexes sometimes can be handy. Now, that's all for mutexes. Let's go for something more interesting. Let's get rid of this code. A special kind of synchronization primitive is a once flag. It's used by std call once to call a function exactly once, even when the invocation can be done from multiple threads. So let's look at an example which will demonstrate this. Let's include our headers. Let's create our once flag, call it simply flag, and our some function f, which would be a lambda. We will call it with an integer and simply print that out. Voila, nothing fancy. Now let's create a bunch of threads which will try to call this lambda. Of course, let's use std call once and pass it the flag. And after the flag, we need to pass the actual thing we want to call and parameters. So this invocation here will call f with parameter 1. So we should see 1 printed out. Let's make a bunch of these threads. Each of these can be called with different values, and let's join them. So what do we expect to happen? We expect one of these threads to win and call this function. Which one? We don't know. But thanks to this once flag, we have the guarantee that only once that the function will be called. Let's see in practice. Thread number 1 won. As you can see, nothing more. We run it again, thread number 1 won, and no other thread managed to call that function. So that's essentially how once flag works. You have the guarantee that the given function will be called once and only once. Going on to something even more interesting. Let's remove this code. A condition variable. So, condition variables are very handy primitives used to signal events about shared data between threads. The use case can be a bit tricky to understand at first, but let's try. First, you would need to have some shared state which will represent a condition on which one or more thread will wait. And this condition should be set by another thread. In our case, please excuse the global variables, but in order to demonstrate it, I will use the most simple example. Let's use, for example, a shared state, a shared data, a string. Yes, good. So we have our shared state between threads. We'll make those threads a bit later. Also, let's include our condition variable. It has its own header. And let's see what happens next. We have our shared state. The act of modifying the state should be signaled to other threads by the conditional variable itself. So, in other words, we have a bunch of threads, we have a condition variable, and one thread will use it to signal all the others, or one of the other, depending on what you do, that something has happened. Let's see that something. Let's create our std conditional variable cv, and let's create a simple log data which will print out our shared state s, our string. Pretty easy, but where are the threads? So let's assume log data will be called from some other thread than the main one. So typically we would use a mutex to protect our shared state. And well, this is what we're going to do, even in the case we have a condition variable. So let's introduce a mutex m. Of course, we need to include mutex header. And let's call it, well, let's lock it using a unique lock. std mutex lock m. This locks our mutex. So in case s is modified from another thread, which we will do in a minute, the mutex will protect it. But that's not what we want to do. We want to use a condition variable to signal that log data method, or function rather, that some event has happened. For example, the data has been set. Before that, the string is empty, and we don't want to print out an empty string. A condition variable has a method called wait. This method takes a unique lock to a mutex which guards our shared state, and the predicate which returns true when our condition is met. Our condition is that the shared state, that the string s is not empty. So our predicate should return true when the string is not empty. Actually, no, don't need to capture anything. So this line tells the condition variable to wait here while the string is empty. And the act of checking if the string is empty is guarded by a lock. Essentially what happens is this lock gets unlocked, so other threads can freely modify a string. And when the condition variable wants to check if the condition to wake up is met, it automatically locks the mutex again and automatically unlocks it after calling our predicate lambda here. So this means our condition variable will wait until an event happens, until a condition is also met, and everything will be synchronized using this lock with this mutex. So now we have a waiting portion or a waiting section. Let's get on with a writing section. You can think of this as a consumer of data and the main thread as a producer of data. First, let's make a thread T, which will simply call log data. It will start immediately, and immediately it will wait for the string to not be empty. So now let's set our data, and let's do it in a small scope, also protected by our lock. Let's say some data. As you can see, this write is protected by a lock. This read and this read is also protected by a lock, so no race condition happens. And since we set some data, we can notify the condition variable about the event. The event of setting data has happened. And condition variable has a notify all, will notify one methods. Let's call notify one because we only have one thread. And this will make the wait method here to unlock and check this precondition, well, this predicate, sorry. If it's true, it will simply return. If it's still false, because there are situations when wait will try to check the condition here even without notifications, then in such case wait will wait longer. So we have our notification of the condition variable that some event has happened, and let's join the thread and see what happens. When we run it, you can see some data has been printed out without any data races. So let's go through it again. We start a thread. This thread waits for the data to not be empty and the condition variable to be notified of the event of setting data. Here we set the data. All of this is protected by a mutex. Then we signal our event. Our condition variable wakes up, checks if the data, the string is not empty, and then prints it out. The thread is joined, and we're happy. This is commonly used when you have producer threads which produce some data and consumer threads which consume that data. Okay, so now let's clear this code and let's go to something called eFuture. Let's include the future header. We don't need string anymore. We probably don't need mutex anymore. Futures are a way to receive the result of some asynchronous operation, or maybe even a simple way to signal an event, a bit other way than using conditional variables. For example, if you want to compute some value in a different thread, maybe by invoking std async or doing it manually, you can use std future as a primitive to pass the data to the calling thread, or an exception if one occurred. A std future is a container for both data and an exception. Trying to get data, well, trying to get the value held by the future will result in the future waiting until the data becomes available. So let's see this in practice. Let's have a future, which will hold a value of type int future, and let's have this future wait for the data produced by std async. Std async pretty much calls a functor in an asynchronous way. Maybe in another thread, maybe it simply defers the execution, but it pretty much means the code will be, for example, return 2, this code will be executed asynchronously. So we have our future, which will hold a value of type int at some point, well, in the future, as the name suggests. And now let's print it. We call future get, which will make the future wait for the value to be available, and then return it. Let's see how this works. It prints 2. Our std async produced a value of 2, which is then put in the future, and we then extract this future, well, this value from the future, calling get. You can also have futures with type void, and futures of void don't hold any values, but you can still set values, well, set empty values on them, which will make calls to get or calls to wait simply be signaled that the execution is complete. This makes them pretty much a universal event notifiers. Yeah, that's the word. Maybe let's see this in practice. We will use something called a promise. First, let's set some data and use std promise of type void. A promise is pretty much something which promises a value will be available, or in case of void, a signal will be emitted in some time in the future, and you can actually take the future from the promise. So out of future equals from get future. And this future here, which is of type std future void, maybe let's print it out, future void, will be notified that some event has happened by using this promise from which it came from. So let's launch a thread. Here let's set i+1, for example, and let's set the value in the future. Since we have void here, there is no real value here being set. We only use that promise as a means to signal the future that we're done. In here, let's call future wait, which will make the future wait until the value is set on this promise. And then std cout, let's print the result. Wow, that's something new. And join. Let's run it, and you can see we have 1 as the result. What we can see here is a perfectly synchronous way of moving value from one thread to another by touching the same shared memory, but without using any mutexes. Simply we use the future to wait until the value, which in this case is void, is set on the promise. So wait then returns, and we can proceed further. So our future here pretty much is a primitive used for notifying our main thread that some other thread has done its work. So these are the most basic synchronization primitive we have in C++ right now. I hope you found it informative. I hope you know what to use in your multi-threaded code. Subscribe, comment, give thumbs up, and see you in the next one.